Welcome everyone to the MATLAB tutorial on process control analysis, design and assessment. Let's take a brief recap of what we have seen till now. We have seen a little bit of system modeling, how we can model the system, and Laplace transformation and its application in both time domain and frequency domain, and the controllers for single input single output systems, mainly PPI and PID controllers. Tuning controller parameters is the topic which we are looking at now. The tuning is finding the best controller configuration that can be implemented in the given system. This can be done in two ways. One is stability based and the other one is performance based. We have looked at the stability based controller using Ziegler-Nichols tuning. Now we will look at the other method, which is performance based controller tuning. In this method we have direct synthesis method of tuning, where we specify the required closed loop performance in terms of GCL. As can be seen in the closed loop transfer function, we can specify GCL and ultimately back out GC. Now one small distinction which has to be noted is that the controller will be implemented on a true process, whereas we can design the controller based on a notion of the process, which is model of the process, that has been denoted as GM here. So while designing the controller, we use the best known model of the process, which is GM. This distinction becomes important as we complicate the structure, and we will look at MIMO systems. Now let us look at how we can do and calculate the direct synthesis method controller transfer function using an MATLAB example. As I have already told you, we specify the closed loop required closed loop transfer function GCL as G desired, and we back calculate the controller transfer function C. Now this example, where I have taken a GM to be 3.5 by 2s plus 3 into 3s plus 1 plus 4 into 4s plus 1, and the G desired is mentioned as here. Based on this, the controller transfer function GC can be calculated like this. The same system has been simulated in the code given here. For that, I have used a couple of MATLAB inbuilt functions. First is TF. TF enables us to specify the transfer function of the given process, and we can perform any multiplication, division, addition, something like any mathematical operations using these transfer function models. So we can calculate the GC as directly G desired by 1 minus G desired times model of the system. The G desired has been the controller configuration GC has been printed out here. As you can see, the calculation turns out to be the controller gain is 2, which can be seen here, and the integral constant value is 7, that also can be seen in the in this constant, and the differential value is 12 by 7, that also can be seen here. We can run and check whether this calculation works out. So as you can see, the process reaches the set point very fast. We can change the values of the desired transfer function here, and then check whether the performance looks similar. So let us change the value tau and run the example again. So as you can see, there is a little bit of overshoot in this graph, and similarly you can do the tuning by specifying different G desireds, but keep it in mind that we are expecting a PID controller configuration. So only if the controller transfer function C, which is of second order, second order, then we can compute PID values. So in some cases it cannot be directly computed. So we may have to define something called a filter and use both the filter and the PID controller transfer function together as a controller configuration. This is an example where we specify both GM and G desired as having a same order of denominator, and based on the definition GC equals to 1 by GM times G desired by 1 minus G desired, we compute the controller calculations, and we find that Kc is 4, tau I is 1.33, tau D is 0.25, but still we have this 1 by 2s plus 1, which we call it as a filter transfer function, and use this in addition to the controller we specify. This is another example which I can show by working out here. So let's say C is 1 by GM times G desired by 1 minus G desired. So that will be 1 by S 2s square plus 3s plus 1 minus 1 times s plus 2 into s plus 3 into s plus 5. So that will be 1 by s into 2s plus 3 times s plus 2, s plus 3 and s plus 5. Now note this, we have third order polynomial in the numerator, whereas second order polynomial in the denominator. So what we can do is we can separate one of the terms in the numerator together with the additional term, which is 2s plus 3, and we can take it out as a filter. So we will have s plus 5, say for example 2s plus 3 as the filter, then we have s square plus 5s plus 6 divided by s as the controller. So based on that we can compute the controller tuning parameters. So that can be computed as 5 times 1 plus 6 by 5 s plus 1 by 5 times s. Now k here is 5, tau I is 5 by 6 and tau D is 1 by 5, and the filter function is s plus 5 by 2s plus 3. So like this we can design any controller configuration based on the desired transfer function, desired closed loop performance which we are specifying. The main drawback of this method of tuning is that we are specifying the required performance. Because of that we do not know how optimal the performance is. The Ziegler-Nichols tuning, which is stability based tuning, there we are more concerned about the stability than the performance. Because of that we backed off to a large extent from unstable regions. Because of that the controller will be more or less stable, whereas in this method we are specifying the desired closed loop performance. Because of that we have to worry about the stability. Till now we haven't looked at any complicated systems, and one such will increase the complexity of the system further. One such system is inverse response system. Inverse response systems are the systems whose initial response is in the opposite direction of the ultimate response. So, such responses can be found in boiler drum, steam boiler drum operation, distillation column, bottom composition control, and crystallization and similar processes. Whenever there are two parallel first order processes combined together to give a output, such processes display inverse response. So, the idea is whenever you give a step input to the system will initially respond in the opposite direction of the final value. So, there is let's take a configuration which is given in the picture here. So, we have k1 by tau 1 s plus 1 and k2 by tau 2 s plus 1, and these are subtracted together to give y. Now, if this is the transfer function of the system and we have tau 1 by tau 2 greater than k 1 by k 2 greater than 1, then the system displays system shows a inverse response. Now, let us take an example. So, let us take 2 by 10 s plus 1 and 1 by 3 s plus 1 as GP1 and GP2, and we will subtract that to get the final process model, and we will simulate it to see how this open loop transfer function responds. As you can see, we have given a step response of unit magnitude. So, the final value also has to be close to 1 or in the positive direction, but the initial response goes in the negative direction first and finally settles to a positive 1, which is expected. Now, this type of systems are characterized by a a 0 on the right of plane. So, any if the system has one or more zeros on the right of plane, we can expect an inverse response. Now, such inverse response systems have show a difficulty in control. So, if we were to implement PID control directly, we may find some sort of performance loss. With direct synthesis, we can specify which type of response we want in closed loop. So, because of that, we'll get a better controller configurations. So, the key idea is to lose a certain amount of performance in order to get stable realizable controller. The main thing to remember is that if the system transfer function is contains at least one RHP 0, say like this, with respect to some denominator, then the closed loop transfer function for any control configuration will have GC divided by 1 plus GC, and let us assume C to be some PID transfer function. So, that will be some Kp into 1 plus tau ds plus 1 by tau is. In this case, there is a numerator of GC will be 1 minus alpha s into Kp tau I tau d s square plus Kp into tau is plus Kp divided by tau is. Now, this has one RHP pole, one RHP 0. So, this on looking at the pole of the closed loop transfer function will introduce a RHP pole on the closed loop transfer function. Because of that, the controller will become unrealizable. So, due to this, we use direct synthesis method to compute the controller. So, here I have taken a system where there is one RHP 0. So, so the system coefficients are given in the system description is given here. So, as you can see, I have given 1 minus 2s as the 0 and numerator, and the denominator coefficients are 2, 11, 19 and 10. So, this controller works out to be having the parameters k to be 3, tau I to be 3 by 2 and tau d to be 1 by 3. So, using this controller, we are going to control the process mentioned in this model transfer function, which is 1 minus 2s divided by 2s cube plus 11s square plus 19s plus 10. Now, let's simulate and check the response. Now, even though there is a initial dip in the direction, the performance is still good, because there are no overshoots as in the direct PID tuning. So, if the process model which we have assumed to be is like 1 minus 2s divided by 2s cube plus 11s power 2 s square plus 19s plus 10, something like that, then the desired control closed loop performance we also define with same 0 which we have in the model, and then we specify other parameters like s plus 2 into s plus 3, something like this. So, based on this, we calculate controller transfer function GC, which is G desired divided by 1 minus G desired times 1 by GM. Now, what will happen is that the numerator of G desired, which contains 1 minus 2s. So, let us do this. So, you will have 1 minus 2s divided by s square plus 5s plus 6 divided by s square plus 5s plus 6 minus 1 divided by s square plus 5s plus 6 into 2s cube plus 11s square plus 19s plus 10 divided by 1 minus 2s. So, these two will get cancelled and these two will get cancelled. So, we will end up with something like 2s cube plus 11s square plus 19s plus 10 divided by s square plus 5s plus 5. Now, we can specify any G desired as we want. So, the main criteria with which we specify G desired is that the gain of the closed loop transfer function has to be close to 1 and the time constant tau of the closed loop transfer function has to be as small as possible. So, remember there is a pole and a 0 cancellation here. This introduces a problem when we have GM which is not similar to the process we are implementing the controller on. The process model can change over time. It can also be very different from the model which we have because of some phenomena which we might have missed while modeling. So, due to these reasons we have to look at how this controller will work for a different process model. Let us take the same example. We have the process to be 1 minus 2s divided by 2s square plus 11s sorry 2s cube plus 11s square plus 19s plus 10, and we have the same controller configuration which is with the Kp value to be 3, tau I value to be 3 by 2 and tau d value to be 1 by 3. Now, how will this controller work on this process is what we are trying to see. Now, remember that we have designed the controller using the same 0 which is 1 minus 2s in this G desired, and we are using the same controller for a system which has same 0 at 2 right of plane of and at 2. Now, let us suppose the GP is assumed to be 1 minus alpha s divided by 2s cube plus 11s square plus 19s plus 10. Then the controller which we designed is s square plus 3s plus 2 divided by s. Now, because of the way with which we have designed the controller using G desired as 1 minus 2s divided by 2s cube plus 11s square plus 19s plus 10, we may not be able to control the system with for all alpha values. So, we can find the limits of alpha with which till which the system can be controlled using by computing the closed loop transfer function of this system. So, let us compute that. So, we will have closed loop transfer function GCL equals to GPC divided by 1 plus GPC. So, which would be 1 minus alpha s into s square plus 3s plus 2 divided by s into 2s cube plus 11s square plus 19s plus 10 multiplied by s into 2s cube plus 11s square plus 19s plus 10 divided by s into 2s cube plus 11s square plus 19s plus 10 plus 1 minus alpha s into s square plus 3s plus 2. Now, these two terms will get cancelled and we will end up with s square plus 3s plus 2 into 1 minus alpha s divided by s into 2s plus 5 into s plus 1 into s plus 2 plus 1 minus alpha s into s plus 1 into s plus 2. Now, what I have done is to just factorize this polynomial and this polynomial. So, we can see that s plus 1 into s plus 2 is common here. So, we can take that out and cancel it. So, we will have 1 minus alpha s divided by s into 2s plus 5 plus 1 minus alpha s. So, we have 1 minus alpha s divided by 2s square plus 5s minus alpha s plus 1. So, 1 minus alpha s divided by 2s square plus 5 minus alpha s plus 1. Now, if we perform Raut-Array test for this denominator polynomial, we have 5 minus alpha being positive. Now, if this is the criteria, alpha has to be less than 5. So, we assumed the alpha to be 2. So, any alpha which is less than 5 can be controlled by this controller. So, we can tolerate error up to 250% of the original model which we have assumed, which is 1 minus 2s divided by denominator polynomial. That means even if the process transfer function is 1 minus say 5s divided by the same denominator function, we will still be able to control the system and get the same performance as specified by this closed loop function g desired. So, the Gp is 1 minus 2s divided by 2s cube plus 11s square plus 19s plus 10, and we have controller configuration which is s square plus 3s plus 2 divided by s. Now, using these two, we can compute the closed loop transfer function which is GPGC divided by 1 plus GPGC. That will be 1 minus 2s times 2s cube plus 11s square plus 19s plus 10 into s. So, there is s square plus 3s plus 2 in the numerator also, divided by 2s cube plus 11s square plus 19s plus 10 into s plus 1 minus 2s multiplied by 2s cube plus 11s square plus 19s plus 10 multiplied by s. Now, these two get cancelled. So, we will have 1 minus 2s times s square plus 3s plus 2 divided by so, let us just do the multiplication so that we can understand the importance of doing this. So, 2s cube plus 11s square plus 19s plus 10s minus 2s plus 1. Now, you can see we have two s cube plus 11s square plus s power 4 s cube s square plus 8s plus 1. Now, we can perform Raut-Array test for the polynomial to check whether there are any RHP poles. As long as we do not have any RHP pole, this transfer function will be controllable. Now, let us suppose the process is like 1 minus 10s divided by the same denominator 11s square plus 19s plus 10. Then we will have minus 10 instead of 2 here, and this term will become 0. So, we can analyze this by replacing this 2 with some coefficient alpha and checking whether this alpha will have any effect on the stability of this process. So let's do that. So we have Gp, which is 1 minus alpha s divided by 2s cube plus 11s square plus 19s plus 10. Now the Gc is the same which we have used here, s square plus 3s plus 2 divided by s. Now the closed loop transfer function would be 1 minus alpha s times s plus 1 into s plus 3, sorry, s plus 2 divided by s into 2s cube plus 11s square plus 19s plus 10, right. So divided by same thing. So we have 1 minus alpha s times s plus 1 into s plus 2 divided by s into 2s cube plus 11s square plus 19s plus 10. Now these two will get cancelled and then we will end up with a polynomial which is like this. So 1 minus alpha into s plus 1 alpha s into s plus 1 into s plus 2 divided by s into 2s square 2s cube plus 11s square plus 19s plus 10 plus 1 minus alpha s into s plus 1 into s plus 2. Now we have to look at the stability of this polynomial. This we can do it using Routh stability test. Based on that, we will find the condition that as long as the phi minus alpha is greater than 0, we have stable poles. Now this implies alpha has to be less than 5, right. So any alpha which is greater than 5 will result in one or more poles on the right of plane. Because of that, we will have unstable controller and unstable closed loop performance, that we can see in the simulated example here. So here I have simulated the same controller configuration and used the same model here. Suppose let us assume this to be 12, or let us assume it to be 6 and then run this code. So as you can see, the system starts to become unstable here. Even if it is something like 5.1, you will find that the system starts to become unstable. So the magnitude of the oscillation keeps on increasing. So we have used 1 minus 2s. So the system, so we have used 1 minus 2s divided by the same denominator as the model. Now we have found out that alpha can take any value between 0 and 5. So because of that, we can say the tolerance of this controller is like 5 minus 2 divided by 2, which is like 250% of the original value. So even if the model which we have identified is 250% worse than the actual process, the process this controller which we have found out using this model is still valid and it can be applied for controlling. So with this I will stop this tutorial. We will look at time delayed systems and further examples in the next tutorial. Thank you.